What does a simple spring have in common with a car's suspension system or even a massive skyscraper? Well, they all follow a single, really elegant rule of physics that explains how things stretch and bounce back. Today, we're going to unlock Hooke's law.
I mean, we've all done this, right? You take a rubber band, you stretch it out, and the second you let go, bam, it snaps right back to its original shape. So what's the deal with that? What's the secret behind that incredible ability to just restore itself?
Well, the answer is actually pretty old. We're talking over 350 years old. It comes from the mind of a brilliant scientist named Robert Hooke. He was completely fascinated by elasticity in objects, and he's the one who figured out the core principle behind how it all works. So, Hooke first published his discovery as a kind of puzzle, a Latin anagram. But what it meant was beautifully simple. As the extension, so the force. In other words, the more you stretch something, the harder it pulls back. It's such an elegant idea, and it's the bedrock of what we now call Hooke's law. Okay, so let's put that into a slightly more formal definition. Hooke's law basically says that as long as you don't stretch something too much, and trust me, that too much part is really important, the amount it deforms, or, changes shape, is directly proportional to the force you're using. It's that simple. You double the force, you get double the stretch. And like all the great laws in physics, this whole idea can be boiled down into one beautifully simple and powerful equation. F equals negative kx. That's it. Just 3 letters and a minus sign, but wow, they explain so much about the world around us. So let's break this down. What does it all mean? Well, F is the force you apply, your push or your pull. X is the distance the object stretches or gets compressed. That little negative sign is crucial. It tells you the spring's force is always pulling in the opposite direction of your stretch. And K? Well, K is kind of the secret sauce. This K is called the spring constant, and it's really just a measure of stiffness. A material with a low K value, like a soft rubber band, is super easy to stretch. But something with a really high K value, like one of those massive shock absorbers in a car, is incredibly stiff. It takes a huge amount of force just to get it to budge. So why does this even happen? I mean, what's going on deep inside the material? Well, if you could zoom way, way down to the atomic level, you'd find that the bonds holding atoms together act just like microscopic little springs. When you stretch a material, you're literally pulling those atomic bonds apart, and that pullback feeling is just them trying to snap back together. Now, this all works perfectly, but only up to a point, which of course leads to the big question, what happens if you apply too much force? What if you just keep pulling and pulling? Every material that follows this rule has what we call an elastic limit. Think of it as a line in the sand. As long as you stay within this limit, the object is always going to return to its original shape. But if you cross that line, you move from elastic deformation into a whole new territory, plastic deformation. Elastic is temporary. It's reversible. The object just snaps back. But plastic deformation? That's permanent. It's irreversible. A paperclip is the perfect example, right? You can bend it a little and it springs back. But you bend it too far and yeah, it's staying bent for good. Crossing that elastic limit actually changes the material's internal structure forever. It really is the point of no return. You've stretched those little atomic bonds so far that they just can't find their way back to their original positions. Okay, so we've got the theory down, we get the formula, we understand its limits. But where does this principle actually show up in the real world? Where is this law hiding in plain sight? The short answer is absolutely everywhere. The coils inside your mattress that give you a good night's sleep, that's Hooke's law. That simple rubber band on your desk, yep, that's it too. Even those old-school weighing machines with a spring inside depend completely on this principle to work. And it scales up in some pretty incredible ways. Engineers rely on this law constantly. They use it to design everything from the shock absorbers that give your car a smooth ride to massive bridges and skyscrapers that are designed to safely flex with the wind instead of just shattering. Understanding this law is fundamental to building our safe, modern world. This relationship is so reliable that we can use it to do some quick calculations. Let's make it real for a second. Let's say you pull a spring with a force of 10 newtons, and you see that it stretches 0.1 meters. How would we find its stiffness, its K value? Well, you just rearrange the formula a bit to K equals F divided by X. So you take 10, divide it by 0.1, and you get a spring constant of 100 newtons per meter. Simple as that.
So let's do a quick recap of the most important stuff. We've got the core formula F equals negative kx. We know it's only valid as long as you stay within a material's elastic limit. And we've seen that its applications are pretty much everywhere, from the simplest little springs to the most massive structures.
So really, when it all comes down to it, Hooke's law is the elegant, simple, and incredibly powerful rule that dictates the secret life of all the objects that stretch, compress, and bounce back all around us.
And that leaves us with one final thought. Now that you're in on the secret of the stretch, take a second and look around you. From the pen you might be holding to the chair you're sitting on, how many things can you spot that are quietly and perfectly obeying Hooke's law right at this very moment?